my wonderful colleague, Nanjo Jun. I've already told you so much about her. Um, we're just doing some final checks. We're starting any minute now. Okay, so Nan.
Okay, so my name is Nan Chuojun, and I'm a PhD candidate from the Hong Kong Polytechnic University, supervised by Professor SiF2022. And I'm glad today to be here to give you a workshop of OpenSees for the application of localized fire model for performance structure fire design. And So before we start the workshop, I will just give you a brief introduction about myself. My name is Nan Zhuojun. You can just call me Nan. And my bachelor degree is civil engineering, and I got my master degree from the University of Edinburgh in structure and fire safety engineering. And after graduate, I work for Arab in Shanghai as a graduate fire engineer. And now I'm a PhD candidate, and my research lies in the influence of localized failure on the global response of structure in realistic fires. And I'm particularly interested in the application of trialing fire and the AI for structure fire safety. So if you have interesting about my research or you just want to discuss more, please feel free to contact me. So let's back to the workshop. Today's workshop will include 4 parts. I hope after this workshop, I could give you good answer about those 4 questions. First, I will just recall very basic knowledge about the Hasami localized fire, and then I will show you how to apply localized fire model in performance-based structure design in real projects. And then let's go to OpenSees. I will teach you how to set up localized fire model in OpenSees. In the last part, I will show you how to use GID to simulate the thermal and structural response under localized fire scenarios. Okay. So the first part, we will introduce Hasami localized fire first. It's proposed by Yuji Hasami in 1996. And this localized fire model has been widely used for both academic research and real projects in industry. And it had been written into Eurocode 1 as Appendix C. And all the key parameters used in Hasami localized fire has been shown in the figure, including the diameter of the fire, the height of the fire source, and the ceiling height, and the release rate, and ambient temperature. Also, the most important thing is we need to know the distance between the fire source and the beam. So after we define all the parameters we used for Hasami localized model, and we can just simply follow the equation from the Eurocode to calculate the heat flux from the fire source to the beam as the fire boundary. And now I will sorry, we might just need to wait a minute, okay? So now I will introduce my worker experience in Europe. Okay, so I work for Europe in Shanghai in the fire and risk group and led by Professor Luo, who is here today. Okay, and I'm as I mentioned, my main work is for performance-based structure fire design, especially for large space steel structures For example, I have been involved in Hangzhou Xiaoshan International Airport Terminal 4 and Winter Star Ice World in Shanghai. So we always choose localized fire model to apply it as the appropriate fire scenario to do the performance-based design for the large space structure. This is because we all know there are some clearly limitation to apply standard fire and parametric fires to this kind of large space structures. So we need to use localized fire to generating the non-uniform temperature distribution for large space structures. And I will show you how we do it in industry. So unfortunately, we just got the Excel to help. This is a tool we use. For example, if we want to do a structure fire design for this kind of steel frame, first we need design the fire scenario first, and we input all the parameters we select for the Hasami localized fire, and then the most important thing, we measure the distance between the structure members and the fire source. And for each single structure member, we need all measure the distance. So just for this simple steel structure, we need already have 40 structure members, including beams and columns. And after we determine all the fire parameter and measure all the distance, we will input all the data in Excel. It could help us to do the heat transfer analysis and got the thermal load applied. Then we apply it to the finite element structure to do the response analysis. But as I mentioned, for each element, we need to measure the distance. And for the real structure, the model will like this. It might have thousands structure members or even more. And we might need to design a number of fire scenarios to make sure we already include the worst fire scenario. Okay, so it will be very painful for engineers to do the calculation again and again, and it's time burning and it's very ineffective. Okay, but the good news is we already developed localized fire model in OpenSees, and you can download this example from our website, which is developed by me, and I will just show you our website. Here, as you can see, you go to the OpenSees website, you found the document, and you can find this example. So this is a real scale compartment, compartment fire test, and the test compartment is a square compartment with height of 3.4 meter, and I-beam set in the center of the compartment, and just below the main span of the beam, a square burner, gas burner has been set in the floor, and one of the experimental results has measured there is around 1,000 kilowatt fire. So I will just show you the TCO we download and go through it. You will have a better idea how we make it works. So as already mentioned by my colleagues, for this TCO, the build structure part and the heat transfer analysis part is quite similar. So we give the dimension definition of the I-beam first, and also we can set a variable to define the central location of this I-beam. Here, we can define the central X as 0 and the central Y as half height of the beam height, and the central Z is a half length of the beam length. Okay, And then we set mesh. In this case, we use 3D heat transfer analysis, and we determine the heat transfer material, heat transfer entity, get the heat transfer mesh, and we set up all the constant for heat transfer analysis. Also, in this case, we assume our I-beam just export to fire only for both three sides. And in this line is what I want to discuss mainly for today's workshop. So let's go back to my slides. So if we want to set a fire model, first we need to code the fire model first, and we named the localized Hasami localized fire model in OpenSees as localized, and we give it a tag as one, because in analysis we might have a lot of different fire scenarios. We don't want each time we change it, we just set a lot of different fire scenarios with number. And after them, as I mentioned, we need to pay attention about the global coordinate system, as my colleague have mentioned today. And when I set up our structure members as here, like I-beam, after we set up and we use the central variables to help us have a better understanding for the global coordinate system, then we can see here in my TICO, the global coordinate system is like this way. And so after arranging, we can set up the location of fire. In this case, we just want to set a fire below at the mid span of the beam. And according to the coordinate system, we can set up this fire in the location of 0, -2, and the center of the Z beam, center of the I beam, and in the length. And after we set up our fire model, we can use the fire pairs to set fire parameters used in Hasami localized fire model. It includes equivalent diameter of fire, fire size, and the ceiling height. And of course, here we use 3D heat transfer analysis. So it's important to define the symmetrical axial first, because in OpenSees, heat transfer is conducted in 2D. And if we want to use a 3D heat transfer analysis, we will use linear interpolation method. So you need to know which axial is used. And then we all know that the smoke effect has not been considered in the localized Hasami localized fire model yet, but the smoke is a very important effect for the far field. If this kind of structure member is not directly exposed to the fire, but it's in the far away, the smoke will be the most important thermal load for the beams. So we can also use the set fire parameter function to rewrite the fire parameters, what we already determined in the fire localized fire model 1. Like we call the fire model 1, and we can change the location, we can change the fire size, and but the last two parameter is smoke temperature and smoke induced additional heat flux. Based on this parameter, we can calculate. It's not like calculate, we can concede the smoke effect in our localized fire model. And I will show you the validation results. It also has been uploaded in our website. After running this TICO, we will see the simulation results is matched to the experimental results very well. That means if we consider all the main parameters and we set it in a good way, we can use OpenSees localized fire model as a good design fire scenario. And as mentioned by Dr. Zhang this morning, we already developed a new natural fire model. In fact, it's not a really new fire model, it's a new function that this fire model gives us more flexibility to address all the fire parameters we need. So in this fire model, we include all the parameters we discussed above. For example, location, fire size, and the smoke effect. The better thing is, in this fire model, we not can only type the parameters in TICO, but it also can loading time varying input fire parameters while external fire pair data. As shown in the example, I always use a fire pair state to load my time varying input parameters. Of course, it's time varying, so the first column always is time. And because we can load the time varying parameters, we can define as much as different fire location as we want. And even more, it can apply for traveling fire if we as long as we change the fire location continually. And for fire size, this kind of function allowed us to add grossing and cooling phase easily. And I also put the ceiling height for us to double check whether this fire has been impinged or not. And the thermal effect has been also considered. So this is the last part of my workshop. I will give you a showcase to let you have a better understanding how we can use thermocouple to connect the natural fire model in OpenSees to the structure finite element model in Git, and to help us do the analysis or do the design better. So this showcase is just an aluminum roof structure, and I simply design a localized fire scenario here. The fire size is 30 megawatt, and the fire duration is half hour. The fire is located in the lower central part of the roof. And these slides might be a little bit hard to follow, so I will explain in detail and hope you can understand. So thanks for Dr. Anwar Arabi. We already have the assign thermocouple function in our Git. So as a structure fire engineer, I always get structure models from structure engineer. It's very hard for us to build our own structure model, right? So now we have a Git, we can just directly get the structure. We just assume we don't need to build up our own structure model. We already get the structure model, and we can use this assign thermocouple function to assign the thermocouple wherever we need. And then the Git will help us to output all the information of thermocouple. And then we will use this kind of information to build up thermocouple in TICO, then use the TICO thermocouple to record the automatically generated for gas temperature as a thermal load and applied it as thermal load to the structure model. So you might feel a little bit confused why I already set up the thermocouple in structure model, and I need to set up the thermocouple again in TICO. So usually, if you got a structure and you assign the thermocouple, you just directly give gas temperature as your thermal load, right? But it will be easy for uniform temperature distribution, such as standard fire, parametric fire. But as I mentioned, if there is non-uniform temperature distribution, it will be very hard for us to input the thermal load manually. So I just try to use thermocouple as a connection to connect the fire model and structure model better. So I need this kind of information based on the geometric of the structure and determine it again and set up it again in the fire model. And then we can use the fire model to automatically generating all the gas temperature distribution for us. So here is a video to show you how to assign thermocouple in GID. And when you assign the thermocouple, you can change the convectivity coefficient and make sure you assign it in the correct interval, in the thermal analysis interval. And you can just select what kind of structure member you want. In my case, I just select all and assign all the thermocouples. And it's worth to mention, when you assign the thermocouple, you need to assign it to the geometric mode, like this. Here we have 69 structure members, so we assign 69 thermocouples, one thermocouple for each structure member, and don't assign the thermocouple in the mesh mode, because the mesh always changed. If you change the boundary condition or section or material, the mesh always changed, but we don't want to always change our setting of thermocouple. So for example, here, we assign thermocouple 2 to this beam. And now, if you assign the thermocouple 2 in this beam in the geometric structure, and then all the mesh in this beam will load the same gas temperature as received by thermocouple 2. So it will be more easy to control it. And I will explain more how to use this function better. As I mentioned, we need to set up our thermocouple in geometric mode. In geometric, the structure means one beam we consider it's like only 2 nodes and with one line. And the thermocouple always set up in the center of the line. That means if we set up one thermocouple for one beam, then the thermocouple will at the midspan of this beam. And we can, if we want to set up 2 thermocouple in one beam, we can use this function. We go to geometry, edit, and divide it lines into with number of division, for example, like 2. And the one line will be divided into 2 lines, and we can set up 2 thermocouples. And of course, we can select where we put thermocouple, and we can combine different methods or different ways to set up thermocouple. So for example, here, our fire scenario is in the lower central part. So the lower central part will be influenced by fire more effectively. So we can set up more thermocouple in this part. And for the far part, far field, we might just set up some thermocouple, or we may don't need to set up thermocouple. And after we set thermocouple, we can go back to the menu and find the GID plus OpenSees. and we just create thermocouple only. We will got all the information in the tcouple txt file. This file includes all the information for the thermocouple. So we set the thermocouple as a device, and with different ID, and this device is required to get the temperature data. Most important for me is we will got the location of the thermocouple. And besides, we can also create heat transfer data only. It will include all the heat transfer analysis information, as mentioned earlier. So after we got the location information I want, we can go back to TCO and go back to natural fire model to set up the herb as the thermocouple. So we can imagine this block is a very thin metal plate. So once we do the 2D heat transfer analysis, we can just assume the thermal heat transfer analysis from this block is just almost the gas temperature. And again, we always need to pay attention about the coordinate system. So it's a little bit different from the structure as shown here. So the corner of this point is location 040 for XYZ, okay? And we can try to set location center, location X and the location Y in heat transfer entity, and we can try to setting location Z in section log in this part. And we input all the location information. Then we set 69 thermocouples. So as a summary, I believe this procedure is quite complex and hard to follow. So I will summarize it again to help you to better understanding it. So we got a structure like this, and we design our fire scenario first, and we can use our new function natural fire model to input the fires to input the time varying fire parameters, and based on the geometry of such structure, we assign the thermocouple. We got the location of thermocouple, and go back to TCO. We set the thermocouple in natural fire model, and then we just run our cases. It will generating and automatically save all the gas temperature in the different folder. So for each thermocouple, it will have a output gas temperature file. I will just show you how it runs, but not in detail. So as you can see here, you see? Oh, not really. So let's try to run it. Because here we just use 2D heat transfer analysis, so we will get the results quickly. And as shown here, each thermocouple will get one output file for gas temperature. And we can copy all the output gas temperature to our gate model and then apply it as thermal load. Then we just simply run the heat transfer analysis and run the structure analysis we will see a great results in post process. So on the 30 megawatt fire located in the central lower part, this structure, aluminum roof structure, collapsed. Okay. So this is the end of my workshop. And I understand it might be a little bit hard to follow. My objective for this workshop is to show, it should make you have a sense about the development of fire models in OpenSees and the development of the Git and how it can make us to do a effective way to do the structure response analysis under the fire. This kind of new function I mentioned has been applied in our research. If you have interesting, you can just follow our publications. Also, you can check our links to get any new update. So thank you for listening.
Okay, thank you, Nan. Thank you very much, Nan. Any quick questions? Yeah, please.
So one quick question. Why do we need to both the temperature and the flux? These two probably should be connected, no? Like at the roof level.
Why we need to consider about smoke effect?
I don't know. I just want to know why consider the smoke effect. You need both heat flux and temperature. I mean, shouldn't they be related or shouldn't they be connected?
No, so it's not we both need smoke temperature and the additional heat flux. Of course, sometimes we can easily got the gas temperature, but we cannot sure about the smoke induced heat flux. So this the last parameter in the natural fire model is to double check whether the smoke temperature is suitable for our analysis. It's not really defined to it. So when we determine the smoke effect in the OpenSees, we have some kind of condition to double check this the smoke induced heat flux while smoke temperature and the additional heat flux. We just do some calculation. It's not we both add all the heat flux or the smoke temperature as some load to the B. Is that okay? Okay.
Thanks.
There's one more question from
Online. What does it say?
can this analyze be performed for members with rectangular cross-section?
Can this analysis be performed for members with rectangular cross-section? Rectangular cross-section.
I don't think
So if you have a member that is a rectangle, can
Uh-huh.
you do this analysis for it?
I think it's okay.
Yeah.
Yeah,
There is
it's
no- Yeah, say it up to the mic.
it's just about the sectional deformation. It's not about this method that can be applied or not. So I think it's okay. Yes.
Any more quick questions while they get set up? Okay, so our next speaker for this workshop is our very own Dr. Shu Dai. Shu has been working on traveling fires for a long, long time now. As you can tell, I am buying time for them to set up right now. Shu has been involved with developing OpenSees for many years. He is one of the original people that have worked on fire models in OpenSees with Dr. Jiang and Professor Athmani in the University of Edinburgh. He's come all the way from the UK to give us this wonderful presentation, and he will be starting now. Shu?
Anwar, thanks for the introduction. My name is Xu. I'm currently working at Birmingham City University as a senior lecturer in fire engineering. Today I'm going to talk about traveling fires in OpenSees. A little bit background about me. So I did my PhD at University of Edinburgh Fire Group, mainly about developing traveling fire models. At the same time, it's about its implementation in OpenSees. We just need a bit more time for setting up for the online people to view. So the online people, they can view now. Okay. I will just start over. Hello, my name is Xu. I'm currently working at Birmingham City University as a senior lecturer in fire engineering. A little bit background about myself and also the work. So this work started around 2015, about part of my PhD work and developing traveling fire methodologies and traveling fire framework. Part of the efforts, on one side is about developing the theory about the fire models with myself as a structural engineer. At the same time, we put the efforts trying to implement the more fancier traveling fire models into OpenSees and to make the end user much easier to use such methodologies. More background about me is did my PhD at the University of Edinburgh between 2013 to 2018 in structural fire engineering, mainly working with Dr. Stephen Welsh, who is a combustion person, and SiF2022, who is currently leading the group here. And I continue my research as a postdoc at the University of Edinburgh on the same topic on traveling fires. And we basically, part of my PhD outcome is trying to be upgraded to a better version of the traveling fire methodologies in the future version of the Eurocode. So that project finished, that's called Travel Projects, finished 2020. After that, 2019 roughly, I come to NIST, working on structural fire testing, this kind of thing, until 2021. After this period, I come to Bureau Happold in London office as a senior structural fire engineer, mainly tackling about optimization for fire protection. So about traveling fires, I want to give you the background in terms of the research, the industry application, and also mainly about academia, how you apply it in general sense. But what I most want to give you is there are many type of traveling fires if you just simply Google it. You need to judge yourself as a user level, what's basically you really need from your end user level. So since this work is mainly developed during my PhD and postdoc time, I would like to give more credits to University of Edinburgh and in collaboration with Hong Kong Polytechnic University. So motivation about traveling fires. So all these efforts, what we are trying to do is trying to identify the uncertainties of fire hazards in large spaces. And so what it matters for structural engineering. You probably say, well, for most of the cases in our design, we just use a localized fire, that's fine. Everyone's happy. But how about when we are starting looking at the history 20 years ago about the World Trade Center collapse, and everyone know there's a fire load definitely is triggering the building collapse. But at the same time, one NIST was doing the post-fire investigation on water treated thermal. As you can see, all the red dots are basically the flame from the facade, and the blue are not visible, and window open once the flame basically impinging the window and make it broken. And the gray ones, basically, there's no fire observed from that location. So this is at 2:57 p.m. And after 8 minutes, you can see the red dots travel to at this level and travel to the other side of the location. If we continue looking at basically the flame spread behavior after another 8 minutes, you can see at the level of 7, it continues spreading. At the same time, at level 12, you can see more white dots. Basically, there's a burnout and the window open. You don't see the external flame. After another half an hour, you can see at the original level 7, all the window broken. You don't see external flame, but the flame at the same time spread to the upper level as well. So you all know, normally when we do structure fire design, we tend to do things very conservative and from structural engineer point of view. And also most of the fire resistance are basically carried out by fire engineers. So, but this type of fire load, it doesn't mean if we don't really design our buildings without such a fire load, it doesn't mean our structure is safe, no matter how much fire protection you are giving to your structure element. So what is a traveling fire by definition? It's basically large compartment fires burn locally and tend to move across floor plates over a period of time. So in general sense, it's a tool. It's for you to approximate your fire impact within a very large compartment for your structure design. There are many traveling fire models basically in academia, also in application. And probably every structural engineer, when they work long enough for fire dynamics, they probably come out with their own idea, say, oh, I want to do this traveling fire model as my model. This is the better version. So, but why it matters? So what's basically the ultimate goal we are trying to emphasize? I want to talk about my traveling fire model, about ETFM framework. So it's in nature, it's a combination of localized fire and zone model. So basically, the key thing we want to drive into a better or more generic traveling fire model is we want to put more fire sensing in. So basically, better boundary for your structure. We know how much fire is burning there, how much fuel load you put, what's your ventilation condition. So you know what type of fire load is impacting your structure. And in the other sense, we want to implement it much easier because once you put more parameters into your model, which means your model do more complex calculations. So you need a vehicle, you need OpenSees basically to program it in to let it use from that sense. So I want to talk about more about its science background, fire dynamics. So imagine this is the ceiling, heat flux distribution. You got a localized fire from generic Hassami's localized fire model as an example. Know that here we are talking about extended traveling fire framework, not really a model. So which means for this localized Hassami, you can replace to any other models, localized fire model as you wish. And for the near field, you can see the local impingement from the heat flux for the near field. For the far field, at the same time, is about using the zone model. So the complexity of zone model, so currently in the market, there are probably more than 100 zone models, and everyone claims their model probably is better than the other as a history. But what it really matters, we are following the general rules about energy and mass balance in a large compartment. So I want to give general information. Once you imagine there's a steel beam in the middle of the large compartment. Once your fire is starting to travel, you got preheating, direct exposure, and also post-fire for your structure elements. So we basically want your structure elements to be examined under such different fire scenarios. to make sure the structure is still resilient under such impact. The casing for ETFM for traveling fires is about its fire different stage about its zone model backgrounds in the large compartments. So several generic stage we want to capture is the first stage. Once we got something burning at the initial stage, we got a plume is developing and a ceiling jet. So oil pressure is pressing from the upper level to the downside. So you got oil pressure is pushing out of the window. If we continue developing the smoke layer or basically the fire field, it continue push down, you got more pressure outside of the window. At a certain stage, you basically got your smoke layer accumulated beside basically your downstand. Basically, that's the stage the calculation sometimes struggles because of the partial differential equation coded into the zone model. At the last stage is basically once it's stabilized, that's the stage we really want to characterize is we got the pressure stabilized at the window size. We got more fire flame at the basically at the upper level and to flow out of window. At the same time, there's another pressure about the entrainment from the opening for getting more air. So once this stage is stabilized at this stage 4, that's the stage we pick it up for our zone model calculation. But all these 4 stages are calculated transiently in OpenSees and trying to capture once your fire load at different situation, how basically your far field smoke is transiently being calculated. In terms of fuel loads, there's another point of view is normally in structural fire design, we say uniform distribution about the fuel loads, but at the same time, once for specific structure elements we want to look at more carefully, we tempted to, for performance-based design, we put more fire load under such some of the structure elements specifically. So for this case, once it's implemented into ETFM, and once you got fire is burning and spreading, it basically gives a linear function trying to capture the fire load distribution, and also it's about the spread. It's trying to basically calculate the heat release rate area about your burning zone. Once you got a lump situation, you basically could has the potential to develop to different fire zones to burning your structure. So I would like to give idealized steel composite building with a core as a general case as a case study. So this is the building dimension to XYZ. I will give another example from TICO code base at the last, because I don't think because this workshop, I think the key takeaways I want to get is about generic understanding about traveling fire methodologies, and to pick up your own one that you feel probably could benefit your design. And imagine this is a large compartment with a ceiling height 3.85 meters. And LC is basically the total heat loss through the boundaries. And also LR is the radiation fraction included by 0.8 as well. And this basically some generic about the compartment situation. And so once we apply this fire model into the OpenSees, what we basically observed at the beginning was basically the smoke layer accumulation. And once the fire starts spreading with a prescribed fire spread rate at 5 millimeter per second, which is a moderate fire spread rate, and heat release rate 300 kilowatt per meter square, and fuel load density. So all those values are basically generic information you use for office building design. And you got visualized OpenSees SiF builder during the heat transfer as an example for structure elements at the far field. So you can see you basically got initially a plateau about the far field temperature is heating up the structure element at the far field because the flame is the view factor is not really seeing the localized fire over there. So once the flame is traveling the central zone, antrim or central core, basically the temperature is gradually building up from the localized fire model. And once the flame is directly beneath the model, basically the steel member temperature climbs to its peak and travels away. That is just an example for one element. Imagine like Nan was trying to emphasize, even for a localized fire model, in real projects, you got so many thousands of elements to do such efforts. Once the fire travels, the situation is not something you can check the distance manually as well and implement every heat transfer by yourself. So that's why it becomes essentially important once you do a more complex fire model and you want to put more fire dynamics, you definitely need a tool like OpenSees to carry all this information into your design. So the beauty of this is trying to, once the fire starts traveling, all these structure elements and also the share elements in the compartments is doing its calculation one by one and separately. So it's doing heat transfer calculation elements after another in an automatic manner. And after that, it's saved all in the data file. So you basically can do things like, if you don't like OpenSees to do the subsequent structure response, you can fetch those fire models, basically all this data sheet in terms of heat transfer temperature for some third-party tools like your own, for example, your company, you got Elsteiner, you can directly use that. You can also use tools like Vulkan, like Sapphire as well. But in general sense, what OpenSees at least could provide you is this generic temperature information from your structure, steel beam, and shell elements temperatures for a large compartments about this compartment's geometry. And the other sense is really in our design, we don't know what is going to happen. We don't know what type of fire scenario, what's the fire load, what's the fire spare rate, because it also depends your ventilation condition. Once your ventilation condition or your fuel load density change, you basically got different fire scenario. So that's why another very important factor is we want to run as many traveling fire methodology, traveling fire scenarios as we can. So we never call it a traveling fire. We also call it traveling fires. The reason behind is we want to do as many scenarios as we can to ensure our structure is resilient under different fire scenarios. So these are basically the central core, a very generic building. And those are the red elements, are the key members we want to assess once I run this scenario. So this is basically another 6 scenario for different fuel load densities in the TICO script once you put in. And as from a temperature or structure engineer point of view, we want to say once we got different fuel load densities and different fire scenarios, how basically different part of my structure elements, how it feels. So as you can see, once we got fuel load density like 100 megajoule per meter square, we got pretty tiny bit of the localized fire is moving around, and also relatively thinner, basically the smoke layer accumulation. Once you push your value to 780 megajoule per meter square, you basically got a larger total heat release rate. So as many fire scenarios as we run, and we basically, from the design point of view, and we got all these onerous data set, basically for our structure, to make sure it's resilient. That's basically the key thing we want to ensure. Like a little bit. So those are basically all your, basically when I show the generic, the schematic about all the temperatures it could build up. So you can see with lower fuel load density, you got the temperature roughly 600 Celsius for your steel members. And once you push it up to 300, you got the temperature roughly to 800. You can also see the difference on the far field smoke temperature from 200 Celsius. It can be pushed up to nearly 500. So all these functions are basically being programmed into OpenSees and trying to do in a generic way, more efficient way, and to really free the efforts from structure engineers to put more efforts on which parameter should tap into the model. Because even if you do that manually, probably 1 week you just run one case. That's very common when you tackle all the Excel spreadsheet, doing all the data coupling from fire models to heat transfer, then to your structure. But this, using OpenSees 2, we can do things in a more generic and efficient way. And here is this case once we couple it to the structure as a general situation. And I remove all the shell elements so we can view it's more in an amplified manner. So you can see on the right-hand side, all the structural elements are expanding due to the far field smoke temperature is heating up the entire structure. And once the fire is continue traveling, we can see at different locations of the structure elements is deflecting. So this is just a demonstration case. It's not really some case we use as a design, I must to clarify. It's just for general information for presenting this case because there's no concrete slabs in this model. And we all know basically concrete slab in general sense is quite load carrying for such buildings. And this is still in high temperature, basically lose its bending capacity quite quickly once the fire is spreading. And the majority is basically carrying by the slab and also beam tend to become into catenary action. I will just drag a little bit. At this case, at the last minute, I think you can also see slightly about the member contraction once the smoke layer is diminishing and you burn away your fire load. So that's basically once your structure elements goes the axial force reversal from large compression to tension. And you probably will still ask, so what? So why I care about traveling fires and why I care about this fire model, traveling fire model, and this framework rather than the other. So what is a good traveling fire methodologies once you want to apply an InDesign? I think the casing is, it is because of more fire sense, more upper bounds, because in general sense, the key selling points for example, like standard fire, a lot of people will say, well, it's safer. Basically, we ensure my structure is safer. But World Trade Center collapse and many of the classical, all this building collapse prove it's not really safe in that way you imagine. You basically want to get a scenario like in traveling fire manner to ensure your structure is safer. So will upper bound for structure fire design for developing your temperature is a better traveling fire model, or it's basically easy to use so I can meet the deadline for my projects. I think those are the elements you have to, as a user point of view, to think. And from that sense, but from my point of view, more fire sense definitely more better, but you have to do it in an easy to implement way. At the same time, about its boundary condition for structure fire design is to what level it cannot do the prediction. But once you say, when you do experiments, for example, you plug in all these parameters, you want to say, will my model roughly kind of envelope or upper bounds of the real life experiments? Will this all basically underestimate? It's not really a model validation, I would say, because due to the complexities we are facing for trial and error methodologies. It's not really doing that. We are trying to apply as many FIRE models as we can. At the same time, once we plug in some real physical numbers to compare with the test to a level it can match, and also to basically not really match to upper bounds to envelope the case. So here I would like to run a case study about how we set up the parameters. I would not go through the TCO case because the TCO case, the parameter are just there, you just type in. All the hard work basically coded behind by the TCO at the same time about C++. So everything is there. More about your engineer judgment about which parameter I should basically plug in. That's more important about how you use and understand the trial errors. At the same time, at the bottom right, just a little bit selling about our presentations on day 3. So we are going to really appreciate organizing and putting all those 3 presentations together. We are going to mainly talking about trial errors on day 3 in the morning from the trial project in terms of experiments for the first presentation, leading basically from University of Ulster in Northern Ireland. And also the second is about the continuation about this, about CFD model to predict the experiments presented from the upper picture. And the third is about by Nan, about continuing applying different trial and error models for our structure response from 2D, 3D, and what's the implication for design point of view. Because as a structure engineer, the other quite important information we want to bear in mind is once we apply a trial and error into our model, we got a nice data set about our temperature history, what it measures for my structures, 3D or 2D. That's basically the question and going to be answered for that presentation. So for this case, so basically, I plug in the parameters I want to give with my best knowledge about experiments and trying to say to what level it can give and put the error bar on that. So for this case, based on the experiment of test observation, I know it's 3.5 millimeter per second. I think the other quite important information for trial and error models currently is for almost most of the models, I think there's another model recently published by University of Liège by Antonio Gamba. It has the capability to do some of the predictions in terms of FIRE spread. But for most of the trial and errors, we basically give it prescribed FIRE spread rate, like based on the literature. It's spanning from 0.1 millimeter per second to 20 millimeter per second. So this is a test observation from 3.5 millimeter. I plug into the model, and fuel load density is 400 megajoule per meter square, based on the amount of fire loads I'm currently carrying. And a heat combustion is based on some of our other in parallel experiment is currently had been done before, about 11 megajoule per kilogram. And the HRPUA is another important parameter about our generic fuel load density to uniform all your fuel loads in the large compartments based on the calculation of fire spread rate. Is the inverse calculation. So all this, basically the methodology, this application, you can find in more details in our website. Basically, if you just Google Scholar, my name, Nan's name, or the PolyU in general, you can find all these publications. And we put opening height 2.9 and opening width as 9 meters. And the other thing is the current zoom model in ETFM is limited to a very simplified, well, not that simple, but still we limit ourselves to one opening. So we have to put it generic if there's multiple openings. There are better zoom models, more complicated, like ozone, CFAST. This is also something you can explore and try to couple with Hasami. There's another way to do it, but this is something I want to give you a general sense about how it will become if we do using a rather simplified firm zoom model. And we put radial heat loss fraction 0.35 during your fire flame, how much basically the energy is losing to the radiation to the ambient. And heat loss fraction through compartment boundaries, I gave an error bar about a range 0.25 to 0.45. It's basically how much of the energy once we're burning something is going to be lost through your boundaries, through your walls, basically ceilings, and also your structure elements, how much energy. I think that's something is going to be, hopefully going to be improved in the long sense in the firm zoom model in OpenSees. But after we put all this information, so the first I want to have a play about the experiments. We basically start the fire at one end and let the fire naturally just spread to the other hand. This experiment and the video credits come to Ulster University, and the experiment we did 2019. The weather was pretty kind of rainy all the time. But yeah, the experiment itself was pretty successful actually. So once we plug in all this information into the OpenSees, you basically have the localized fire development and also smoke layer accumulation at the far field. So that's basically once we put in, we want to see to what extent our ETFM can behave compared with the experiment measurements. For these experiments, one of the key things we measured are the steel structure elements for the steel beams. So there are many measurements like the heat flux at the surroundings and heat flux, basically incident heat flux, we put significant kilometers at the field bed level. And also about the temperatures from the ceiling, from the wall, and also for the structure elements for the beams and the columns. So here I'm going to present basically the information about the key beam members at the center. So these are the ignition locations, and those are basically all the thermocouple temperatures put at the basically this beam member at the mid span. So here's the prediction or basically about the calculation from the ETFM. Just want to emphasize again, it's not really something we want to validate the model, but we want to benchmark the model against the experiment, trying to say, once we plug in those numbers, to what extent it can overshoot or underestimate. So from the basically the top left, you can see once we put some generic uniform fire spread rate as just one number, we definitely from temperature offset point of view history, we definitely got some temperature difference. Probably especially for the initial ignition stage, we got the temperature offset. Once the fire travels and continue to later stage, I think the model behaves better. But in general sense, the gray bands are basically the information once we put a range as for the thermal load loss through the compartment boundaries. The key information here I want to say is ETFM, currently the model in OpenSees can provide more or less like alpha bounds to envelope the real case scenario. We want to be conservative, but at the same time, that's something I want to address is we also want the science in. We definitely don't want to put something like a standard fire, for example, moving from one location to another. That's something we don't want to do. But at the same time, we want to do something like we basically respect the compartment situation for the opening, for the ventilation, for the thermal loss from the compartments as well. So here is basically my last bit about the example script. So this example script is basically the Trafar model. So the history about ETFM, later on we got different fire groups around the world working together about Trafar project. That project started as a European funded by Research Fund for Coal and Steel as a large project, basically led by ArcelorMittal in Luxembourg. That's the largest steel industry leading this project. And we got partners like ourselves, University of Edinburgh, and University of Ulster from Northern Ireland, and also RISE SP, basically from Sweden, University of Liège from Belgium. So all the team members working together to contribute the experiments, model development, and trying to drive another version of the trial and fire model called TriFire into the work. So this is basically example, but the fundamental thing are similar. I think TriFire basically implements more scenario about more zones, about localized fire. Once the fire is not impinging, what's happening? Once the fire is impinging to different column members, what's happening? So during the ETFM stage, as I introduced at the very first version, it's still a generic framework. So for the TriFire, it becomes more like a model, is trying to do something more specific. But at the same time, there are some other models, like I mentioned, like from Antonio Gamba, there's another version of the model, or some other teams like Imperial College were really leading the efforts for developing different fire models. And University of Queensland, at the same time, they're also putting these efforts. So once we basically, I just want to give it a quick go about what's the meaning about this script. So first, we basically wipe out all the storage, and we set up a data directory just for saving oil files called TriFire example. And because when I was coding those stuff into C++, by that time, we were very keen to develop something to automatically couple the fire modeling, heat transfer, and structural response in a generic way. So one direction currently is ongoing is basically the work by Anwar, and Nice was showing basically the efforts trying to use Git. So that's basically one direction to like Sapphire, basically. You use user interface, you click just based on all the information you want to have and assign your fire boundary condition for that structure element, and you do your case. And the other direction before this we were trying to work on is trying to quickly generate your structure in a generic way and run the fire model and say very quickly, can you make sure or guarantee or get a general sense of your structure response in terms of thermal, the structure response, or the temperature response from your beam members and concrete shell members, basically. So the SiF builder, basically, we define frame. We can also define with concrete as well for shell elements, but this is just for demo because I want to say basically the structure is once it's expanding and also the column is basically expanding in upwards, everything is amplified. I know basically the model is doing the correct thing, and it's also for demo purpose. And we define the SiF X bay, Z bay is basically in terms of the compartment direction. So each number represents basically your bay information in unit of meters. Like my first bay is 8 meters, next is 7 meters, 7 meters again, then 8 meters. And Z bay basically in your plan view is the other direction you define. And SiF story is basically your compartment height is 3 meters. And then we basically define your temperature library about we use the steel about you basically tap in your general steel information like its Young's modulus value like 210 gigapascal. And you define also your I section about its information, and you assign all those I section information to your specific X beams you just assigned. Those information are basically a preparation for doing your heat transfer and also your structure response as well. A key thing I want to emphasize is in OpenSees is not really one person's work. So this work we started in I think as early 2009 OpenSees, even I was still doing my undergraduate, to be honest. And by many generations of PhDs were doing, and now some of them are professors at some universities even. And those information, for example, the heat transfer part is also this information once you define your I section at different locations, and Strcutures&Fire model is trying to seek that location and do the heat transfer for that. But that heat transfer elements were basically done by Yaqiang, like back in 2010 or 2012 at this time. So then after his work about validation, verification, passed on to another generation, we want to apply more, like my generation, about putting more FAIR models. And like Li Ming was trying to put more efforts in the sense of put a wrapper to put it more generic, much quicker way to do the calculation, to put all the information together. And we basically also fix joints or the loop Y. We basically trying to fix all the boundaries for, we want to fix all the column to the floor. We could also define it as a pin, depends on your, but basically that's the SiF builder currently have. At the same time, if you come to more generic, you can also to define semi-rigid, but that function hasn't been implemented yet. And then you apply all your member with the load and also the direction. It's basically the UDL, you put your members to the downwards. Then we add the fire load. So that's basically the key thing for Strcutures or ETFM. So we first add fire at floor level 0. You can also add multiple fires based on your information, and you define your ignition line at one end. It's basically 2 pounds. You form a line to ignite your basically your fuel loads, and the fire travel direction you can define based on your structure. You can define it anti-clockwise. Is basically wiping out basically the fuel load from one direction, or you want to do it anti-clockwise, depends on you, because based on your performance-based design, different locations you want to assign the Strcutures&Fire also decides your structure response and your design interest. Then we go to the fuel loads. It's basically RMFD is trying to do things is about your generic fuel load uniformly distributed at the fuel load level. And the fuel-based heat, you can offset basically the fuel to different location, because quite often we want to set up to the number 0 basically on the floor, or want to lift it up a little bit, because you lift it higher, you're impinging much more to your structure elements. Then we go for the generic fire spare rates, is unit in millimeter per second, and fuel load density following the Eurocode, we give 511, and HRPUA is also a number very generic for office buildings. And we do the mesh control as well for the subsequent structure. And then the bottom bit are basically want to post the view about once it's doing the fire modeling and heat transfer part in OpenSees, want to see its response. This is something about we want to record specific number of elements about its displacement, because that's something when we do structure fire design, another information we want to get is to what extent to judge my structure failure. If we want to pick up specific points to record its deflection or deflection rate, that's probably a place we want to see its collapse scenario about its deflection rate is doing something, and we can just mapping this information to the report. This is the information for doing its heat transfer at different locations. About shell, we basically pick up 9 pounds uniformly distributed with 1D heat transfer. And beam column elements, we use another 15 elements to do 2D heat transfer. There are also better ways for doing it, about 3D heat transfer in OpenSees. But for the efficiency point of view, in SiF builder current version OpenSees, I didn't really trigger that part. I just simply for several 2D cross sections and trying to mapping those to the elements together. And this, once you run the file, you basically generate a bunch of files in your folder like this. Like what I said at the beginning, like another work currently in collaboration with Dan is we run all those different fire scenarios. We generate this basically all the temperature automatically for those generic structure. And we fetch this information using LSTANA even to pick up. And we just wrote like a middleware using Python, less than 100 line of codes. So the information can be bridged from OpenSees generated member temperature directly to LSTANA. So you don't have to do quite complex and fancy FDS or some other scenarios. You can also do things like this different with coupling. And the other thing I want to address is you want to, once you do the coupling, another principle you probably want to get is the level of consistency about your model. So once you run your fire model, you definitely don't want one hand is very complicated for your fire model like CFD, but the other hand for your structure, you simply put one generic beam member over there and trying to analyze it. It's something, but to what level it can benefit your structure analysis, that's something you should ask question mark yourself. We want to put consistent level of complexity, like the fire model is roughly generic, your heat transfer is simplified to middleware and bridge your this kind of not every element is a detailed FEM model, but a generic structures. I think that's something once you want to build up your efficiency for bridging the same level of complexity about information. That's something from the upper level you have to bear in mind. You cannot really do a very fancy FDS at one hand, say, oh, show to the clients, or your two supervisors say, I did really marvelous work for the fire modeling, but you apply it very poor on the structure. You basically pick limited information. So it's a waste of efforts as well. So it's not matching. So you have to strategize yourself for different softwares basically you are using. And this is basically the information on the left-hand side, the plan view. You define basically as the TQ scripts for your temperature spreads. And at the terminal end at OpenSees, you basically say, you can say, basically the heat transfer is doing which compartment. So it's doing one set of compartments for the elements one by one. This is just some quick demo about at the beginning about the fire heating up. The localized fire is starting from here. You can see the deflection about the column and also the beam member, and the column heated up is trying to push up the members. So if I put the shell and the concrete and also the load on, you won't really see this kind of amplified effects. You can see continuously once the fire spread about its spreading effects is continue. So yeah, that's all for my presentation. Thanks. Thank you.
Quite the intensity of information here. We have some time for questions. Are there any questions online as well? Please check for me. Questions for Shu? No? Everything is so clear, Shu. Well, what do we have any questions online? Okay, if we don't get any more questions, thank you so much for your time, Shu. And of course, Shu's around. You can just talk to him. If you have, we will be having another tea time right now. And so we'll be back here in another half an hour. So thank you, everyone. Online participants will be back here in half an hour. See you soon. 3 minutes from now.
Perfect. You managed to get some sleep, sure. Barbara, all right, then make sure you sleep well tonight.
Yeah, I'm still
Jet lag? Yeah. And what time is it now? 7 a.m.
yeah, this morning.
Oh. Well, glad to see you here. Welcome to Hong Kong again. You haven't left for a while, right? This is your first time back in China in 2 years.
It's because of the food. 没有。
Yeah, we have new food delivered.
Oh, so it's very deep rather than.
看这个呢，可以。我说这个退出来。
拿哪个能到哪个拿哪个？哪个是
这个是分享的，
这个吗？
对，你就让他分享下去。他这个，
哎，让他现在就把他的 screen 先分享过来吧，就哦，把他那个推出去，share screen。这脾气好。有啥用？让你发 SiF。对，加了，我好像加了，在群里告诉他就好了，我也没加。我想上去打一下东西。
如果要用自己的电脑，试一下。
Hello to you.
Hello, Atif. Can you see?
Hi, how are you?
Oh, I'm a little nervous now.
Yeah, I'm at home. I'm taking my tea break too. Good luck, all the best.
Yes, I will try my best.
Yeah, good. That's what is needed.
Yeah.
You will do great, I know.
我是下午的话是Atif 是3:45。
3:45。
嗯。
对，你是3:40。Atif,
Yes.
could you please share your screen and PowerPoint when about 3:30? 3:40. 3:40.
3:45. Yeah, mine is 8:45 now.
Yeah.
Give me 2 minutes.
45. You can show it at 40.
Yeah, I will share this. Give me a minute.
可以迷你吗？我是动词。
Okay.
What time in your side, Atif?
8:20 p.m. 5 hours.
Okay.
So can you see my my screen?
Yeah, we can see.
Okay, you can see me as well.
Okay. 这个上面一个啊，我的名字没有了。哇，Atif。
Yeah, it's quite late here.
Yeah. OK， 我先试一下，简单试一下。这样子的话，应该就可以了。然后，诶，图片为什么没有？哦，不行，它有动画。我这个电脑吧，这个 CC 的电脑。我用一下 CC 的电脑的。我的电脑的电源线不够插到那边，我借一下你的电脑，因为我不可以，我是 Type C 的，你是吗？哦，可以，我是那个，你把电脑用你的电脑，对，到时候因为我的，它如果不插电就会反应很大，然后我考到桌面上电脑还有一个高级。
Okay, Atif, can you show your PPT? Show your PowerPoint.
对，我在。
Are you not seeing? Can you? I'm already sharing.
哦。
对，到时候把电脑插着。我先考一下。
It's okay?
Yeah, it's okay.
这个是 USB 吧？这个可以吧？对，我待会儿试一下你的电脑，因为它太远，我电源线不够长。我试一下。
这样子，Atif在这儿。对，Atif在这儿，PPT 在其他地方。
两个空格哈，这个理解。两个。大家可以看这个。
你直接加到那个 section 里面。我中有点多。
没关系，我就。
创建一个新的文档。
直接抽过来也是可以的。应该不用了，用了吗？
对，一会儿你需要加到那个 section， 然后你就 share。
我不知道为什么我用这个，它的有些图显示不了。我先把这个能识别了吗？
可以是对
不是，
对，应该是这个不是
它的音节儿，
这个是吧？
对，我那个 A 键有点问题。
哦，我得先看一下能不能显示出来。
presentation now.
After
A nice presentation.
我先识别一下。
CC, it's you.
OK，然后你是不是需要加到会议里？哎，如果你加了这个会议了的话，我就是要来的时候，它还会出现需要开机什么之类的吗？
不需要。
哦，就一直在，那就让它在这吧。
先把声音关掉，因为这个可能会放在这儿。
那我的话还需要开声音吗？
对，你不用，你也不会拿着那个讲。
这个，那你就不调这个 camera 也不用对吧？
camera 不用，它会去，我们是看那个上，它会直接照。
啊。
他给我一个口诀，然后让他 share 屏幕。重开。
好像下午是一个新的会议。
算了，我不动了。你反正肯定这个之前你已经考过了。
考过了。那我到时候是怎么弄？就直接
share 屏幕，就是这里。小屏幕。
选择这个。
选到这个上面，然后 share。
OK。
如果你想有 case 的话，
没有 case。
好，那
我就只有这个。
那就这个。我们先把它放在这个地上，到时候用的时候就把它拿出来。我上面其他东西我不懂，在后面这个可以关掉，就 PPT 吧。
我到时候直接这个就可以
放到你的手边。
OK， 好，谢谢。
最小化，然后到时候你讲的时候你再 share。然后点击 PPT， 然后共享就可以。
然后我就可以
拿麦克风讲。
这个是吧？
对，就是那个。
OK。
然后记得把它打开，还有个对。然后现在用关灯。是你的电脑。
对，我的电脑。
我就放这儿。
好，到时候我就上来给你拿这个。
直接发过来。
好，谢谢。
没事。
可以。
我还是加入到那个。
对，你自己搞吧。
And the way the thickness of your basically you are it's like
It's like this. Yeah. But in the end, one day I speak like family, the nobody takes like 4 or 5 days. 5 days to be higher than 4 or 5 layers.
Really?
Yeah. I'm the audience.
Now. Okay. So good afternoon, everyone, and I'm Ding Qiu. Now I will show you how to model computers labs in Fire within OpenSees framework. I will present it from the following 3 aspects.
Yeah, you're doing very good. Maybe remove the mask, it will be good. People will see your face if you remove the mask.
Oh, okay, but I don't know whether it is allowed to that we don't wear mask. So I think I will wear it because everyone wear masks now.
Was non-wearing mask? None.
None didn't wear mask.
Yeah, yeah. We also don't have to wear. And
Oh, really?
Yeah. And we're
Oh.
also did not wear.
Oh,
I guess in Hong Kong it's needed to wear mask.
what? What did you say?
In Hong Kong, it's needed to wear mask even in presentation. Otherwise, people can say something to you.
Yes.
Yeah.
Yeah, missing you.
Yeah. How are you?
I'm fine. Can you see me?
Half. I cannot see your face.
Where is camera?
The
I
camera?
don't know.
The camera? Oh, he can see us now.
You can see me. Wait a second. You can see me.
Yeah,
Okay, here I am.
hello.
Hello.
How is your?
Yeah, so I'm home now.
Where is camera?
That camera thing.
I can see you full, but I can see until your shoulder.
Because IK is too tall, so
Yes, now I can see you. Yes, here. Yeah,
that is camera.
yeah, now I can see. How are you?
Yeah, I think. Oh,
Good. Hi, what happened to Moog?
Look, they came back again.
They missed something or something is when they want something.
And asking all links for the third-party videos I used.
Oh, third party is mostly YouTube, yeah?
YouTube, I removed all YouTube videos and I bought copyright-free videos from iStock.
Mm.
Uh,
Wow, but iStock is quite expensive, you buy.
Each video 60 HTV.
Oh, then it's fine. Okay, cool.
so you are still working on the MOOC.
Yeah.
Unnecessary sometimes. And what about that bridge one?
Which?
Bridge video.
Video.
Bridge video which Asif was asking.
They were asking a lot of money. Asif didn't say anything. I told him that.
I think we can make by phone, iPhone.
Yeah.
Because that don't need for approval from EDC or somewhere. I think iPhone is strong enough to make that. And even you are a good photographer now.
They are asking 2000 SKD for renting teleprompter. Right.
Oh, I have teleprompter here. I bought everything. I have teleprompter. I bought mirror as well. Yeah.
Shows your office.
No, I'm at home now. It's 8:30 now.
8:39.
Yeah, 8:30 p.m. So I actually come back around 3 so that I can take some rest.
Okay. Actually,
Sorry?
you are speaking to everyone.
Yeah. Can it customize to one person?
I am standing in the middle of the room and speaking.
Yeah. Can it customize that I talk only one person?
Oh, I don't think so. Anyways, no one is in the room. Right? It's tea break now.
Yeah. I think it's about to finish. So let's catch up soon if you have time about something.
After this weekend, next weekend.
Yeah, sure.
So you settled there now, completely?
Almost actually at this moment I'm living university housing, but next week I will move. So yeah, then trying to be settled down. Yeah, it's easy to there here. Only the transportation is not very good compared to Hong Kong.
So buying a car.
It's needed. Without car, it's very difficult to survive here. You need car because if you got transport, they have only bus and you have to walk a lot to get the bus. Yeah.
Get a bicycle. How far is it?
Bicycle is good. Here, bicycle is you can almost all city you can travel with a bike. Yeah.
The small one. People
Yeah.
go right. Like
Yeah. Okay, see you. Talk to you later.
Bye. Yeah. Can you sensei to check tomorrow? We will not be. It's a different chart. Yeah. Would you like to come with me now, or we can do it? Hey, Atif. With you. Hello, Atif.
Yes.
Could you please show your point, your screen?
Wait a second. Yes. Can you see my screen now?
Yeah. Okay.
But I can see myself as well in the screen, one screen.
You can see yourself.
Yeah, I can see in near podium. There's a TV near podium. I can see myself.
Yeah, that's a TV to show your.
Okay.
yourself.
Okay. Okay. Now I understand what were you setting at the time during the break.
Okay, now it's okay.
Okay. Cool. See you soon.
Thank you. is the basically this professor. The senior professor is not my I'm from originally from Jordan. You're from
Atif,
Yes, yeah, hello.
teacher.
Paul?
Hello. Yeah. But we won't see us then. It's fine.
Stupid things. Fucking accordance with the statement systems. See, it not really possible. Actually, this is
你弄好了吗？你的
我弄好了，我用 CC 的电，到时候我就直接把他的电脑装上。
？OK，那就行了。然后你就 online，然后你不需要开你的开吗？
就我直接 online，然后直接 share my
然后你
screen。
就可以看。
listen to my vehicle. And I think then we want to go to the that's like
Okay. Yeah.
they have one specific. Don't speak dance. Because of fees. They are. Okay.
Hi, I keep
Yes,
the look handsome.
Good. This university. They give me this. Or my university can give me. Yeah.
后来出国后好像23号。
Discuss how can I. You got. It's a It's the one that Before I even finish this experience.
Hello? Chill, what is getting delayed?
Yes, I think so part. Okay, I will ask now.
Bring the participants. Bring the people from outside. Hey, handsome, how are you doing?
Well, hi, I'm well. How are you?
Good.
Yeah, it's quite.
Oh, yeah, we have a,
Yeah.
sorry, a large screen showing your face in front of everyone.
Yeah, I saw that one. I saw. I can see that. I think you need not to put that one. Or I should shut down my camera.
No, keep it.
So yeah, people will know who they are talking to. Who are they listening to?
Okay, we're just waiting a second for some people who are still.
Sure. Take your time. Just let me know when to begin. Yeah, because my presentation won't be that long. I don't think it will take 45 minutes, maybe 35 minutes. I put some time for questions. I hope there are some.
Ife, is our sound on? Can the online people hear us?
Yeah.
Okay.
So can they hear me well?
No, it should be the co-host.
Hello?
Hello?
We can hear you in the room, but let me check the online participants if they can hear you.
Oh, sure.
We still have many people outside? No, everyone's here? Okay, I wait a bit then. Right, we'll begin shortly. We are just waiting for some people who are not yet here.
No problem. Take your time.
This will be the last session of this workshop. We will have our colleague, Dr. Atif Ali Khan, joining us all the way from New Zealand. And finally, we'll have our very own Jin Chio for doing a nice presentation on composite flows.
Bro, everyone's still waiting.
Okay, Atif, I think we shouldn't wait any longer. I think you
Okay,
should
fine.
start. Okay.
Yeah. Okay, I'm going to start. Hello, everyone. I'm Atif Khan, and thank you very much for joining this workshop. And of course, this SiF2022. You're most welcome. But I'm not there for. I'm also doing it virtually. Anyhow, so you already gone through a lot of in OpenSees until now, more than 5 hours, I guess. So I'm glad you are still here. So in this presentation or this part of the workshop, I will talk about OpenFire. What's OpenFire? It's also an integrated simulation tools where you can understand how the structure respond to real fires. Here, real fires we're talking about where you talk about more science like FDA, any CFD based fires. So we'll go through it. So before we go further, like as a structural engineers, most of them, we know that why we are doing structure fires, but it's good to repeat it again. Like we know that fires are occurring everywhere. And according to a study conducted by NFPA, it was like around 500,000 building fires are reported each year in the United States only, and that cost like $10 billion. But this is not limited to the structures are not limited to buildings. There are some bridge fires, tunnel fires. So there are also structure in terms of the bridge fire. Sometimes indirect cost is much higher than building a bridge again. For example, this disruption of traffic, changing the traffic routes. Sometimes the cost is much higher than the building a bridge. So now we understand the heat, why we need to know these structure fires. So what kind of fire scenarios we need to understand the structural response analysis to carry out how structure will respond to the fires, which I think we already went through about localized fires. Shu talked about traveling fires. And most of the time we are using code-based fire, for example, idealized fire like standard fires, parametric fires, and idealized non-uniform fire like Shu talked about traveling fires. They're also idealized. They're not talking about the realistic. Sometimes they are having a lot of assumptions. They are simplifying model. And so they have some limitations to present the realistic, but they are being used for performance-based design as well. But when we have to analyze the building for example, for forensic analysis for WTC towers or Plasco building in realistic, when you want to present a different design scenario for performance-based design, you want to present your client the realistic fire. So you may need some different method which can represent the realistic fires, and CFD simulations are the most viable way at this moment. So I will emphasize again why sometimes we need only CFD. If we want to do to understand the realistic how the fire behave, that conducting experiments may be very costly. You want to do these simulations. You don't want to carry out the very large buildings experiments. Sometimes they are not even feasible. Like tall building fires, how you can get these experiments again and again especially when fire, which is very uncertainty are too high that even you cannot repeat the experiment, result may not be the same. So in this case, CFD is the again most viable options. And this fire model, which we idealized fire model, which are using for designs for standard fires and parametric fire. Sometimes we do not have material information, how the chemistry composition, how the kinetics happening, how the fires, we do not have this information in these models. And most of these models are limited to ventilation controlled. If we see this Thomas curve, now when we talk about the field control, which is usually when you have a large room, fires might be fuel controlled. So it varied from the normal trend. So most of the models we have usually ventilation controlled. And there again, another thing is there's no information of distribution of fuel, how it's distributed. Like for example, you are sitting in this room. If you change just the location of the tables and computers and then anything, the fire behavior would be completely different. So this is the uncertainty which these models cannot tell for this truck. And again, as I tell that if your client is asking for they want us to different fire scenarios for their performance-based design, then you may have to create different scenario using CFD results. So this is why sometimes we need CFD only. So for CFD, one of the most common tool which has been used is named as FDS, which is Fire Dynamic Simulator. I think some of the structural engineer may not be aware of that, but I guess most of them are. So FDS is the CFD tool which is used for fire-driven flow. It's mostly used for practical problem or for research problems. So it solves the governing equations for conservation of mass, energy, momentum, and species. So it definitely solves the conservation of energy. So you get the thermal boundary condition based on, or you can say more science, as she was discussing. Sometimes you need to know more science, and especially when you are designing performance-based design, the client may ask to present with the science. You can explain that with the science, with less assumptions, less simplification. So you may need these. So what is FDS? FDS sometimes requires an input. We usually written in a text file. So it has all inputs of the geometry and fire species and ventilation conditions, and the material, all information is there. And then you run the engine, FDS engine, which may take very, very long time. It depends on, of course, this time will depend on how big your model is, what is your mesh size, and of course, what computers you have. What is their CPU and what GPU. So based on that, when you will get these results, and then you will get the output. It looks simple. Of course, making this file is not very difficult, but as an engineer or as a designer, you have to be very careful when using FDS. It works as a black box. You really don't know what is going on inside. So like it's a CFD is a controlled volume. So if you just change one parameter, the result might be completely different. So as an engineer, as a researcher, you must be aware what you are using and which conditions you are using. You even must be aware what the default values of FDS is. So whenever you are using FDS, be very careful, especially sometimes because running software is easy. It can give you very beautiful contours, plots, but you have to be able to understand how you are getting these results and how we're going to apply for this, especially for a structural engineer, because as Shu also said, that sometimes this is a work of not one person, it's a work of multiple persons. And when you want to do a structural engineering, you need fire engineer and you need a structural engineer so that they can collaborate and can work to understand the problems more clearly in different perspectives. So to understand, to use CFD results with the finite element we are using like OpenSees, we developed a tool which is known as, or package, which is called OpenFire. So why OpenFire? Is an open source, and of course it's free free for distribution. You can buy without license. You can use, you can buy freely, and you can use that one. So whenever using a finite element tool with the CFD, first thing you have to carry out the FDS simulation or CFD simulation from the FDS model. After conducting FDS model, the data is to be transferred to a heat transfer model where you can conduct a heat transfer analysis based on the data you get or thermal history you get from FDS. And from this, after conducting heat transfer analysis, the data can be transferred to a structural model, which is seems very easy, but it's a quite tricky problem, mainly because two reasons. First is spatial discretization and the mesh we are using. The mesh size in CFD might be much bigger than the mesh of even a structural component. For example, the flange and webs might be very small, like in the size of 0.1 of 10 centimeter, 20 centimeter. But sometimes the mesh size would be like 0.4, 0.3, 0.2, depends on your mesh sensitivity you will do. And and you don't want to spend a lot of time for simulation, so your mass size can be higher. So fun is spatial, and another is temporal discretization. The change, because CFD is a fluid dynamics, so change in temperature or change in any quantity you are calculating varies very fast compared to solid elements. So change in temperature in the compartment would be much higher than the solid. So you have a spatial and temporal discretization. So to solve this one, we create the middleware so that we can transfer the data from different parts, and we can conduct, or we can take and extract the FDS data and can conduct the heat transfer analysis as well as structure analysis. So I will explain this figure more clearly in the next here now. So first, you have to develop a model, the structural model that you can use the gate, which I think Anwar explained in this session, or you can use just a script file. I think one thing I want to make it clear, the original version of the OpenSees and FDS, they are actually script based. You have to write a script in FDS. Usually script is written in Fortran language, or you can write in a text and just run in FDS. And OpenSees, you use TCL files, but you have to write the scripts. So once you build a structural model in either way, you will get the information of the nodes and elements of all structures. Sorry. And then this data has been taken by the middleware which we develop. The middleware takes these nodes and and the user put where he needs the thermal data at which location. Like I say, is a spatial discretization. You need like every 0.5 meter, every 1 meter. You can provide this information to the middleware with location. So it will create the 3 scripts for you. It will create the FDS devices, means where you want to take temperature data. At the same time, it will create the heat transfer script file. So you can do heat transfer from that file. So it knows which location this heat transfer is going on. And same time, it will create the element sets. Element sets means the location of the elements where this thermal data has to be provided, the location. So it knows, so from the beginning, you know where your temperature data will go in the structural model. So now you have FDS devices, you transfer to the FDS file, script file, and carry out the fire simulations. And these fire simulations, you get the output in the format with the which FDS gives. Generally, it gives you in a CSV format or slice and boundary file, which I won't discuss here. That will become more CFD stuff, more FDS presentation rather than CFD plus OpenSees. So after get you output in, for example, in the CSV file, this middleware can convert in the format which OpenSees format. So it get the output in the format like time temperature histories in the format which OpenSees can understand. So now we have this script file which we already created, and now we have FDS output. So then you can run heat transfer analysis in OpenSees itself. After running this analysis, you get the output from and now this heat transfer output knows that which element set this heat transfer data has to go. Now you have both data with this element set which already created in the beginning, which will add with the heat transfer output. And from that, you can carry out the thermomechanical analysis. So in this way, this is a sequential analysis. It is not the like two-way coupling, it's a one-way coupling. Two-way coupling is when if you are changing in a structure, it's automatically going to FDS, but we are not doing there. It's a one-way coupling, so it's a sequential coupling. So you get the data from FDS, conduct heat transfer analysis, and from that, you carry out the thermomechanical analysis. Okay, now we are good to go. So this is what I think OpenSees entities, which is we already, I think in previous presentations in the beginning, you know about the heat transfer. So for example, if this is a column and you want temperature data here, this arrow you can see. So this arrow, or means this is, for example, this is a FDS device. So we know that which elements this arrow is representing. So these points, we call it element set. So we know we get the temperature on these elements only. But if you have another device, so it will automatically the middleware already knows that which location your temperature is taking. So this is how this data mapping has been done using middleware. So, but when you are developing this using FDS and OpenSees, I have to make it clear a few points to you. First of all, in FDS, you will using the only fire room. Like for example, you have a 10-floor building and fire is only like a 6th or 7th floor. So in FDS, you will use only 6th and 7th floor. You will not put whole model in FDS. Otherwise, your simulation would be crazy. So therefore, to map the data clearly, your global coordinate should be the same. Means your XYZ of both models and the location is showing in FDS should be the same as in the structural model, so that data mapping can be done easily. And second, I'm mentioning is because I had this problem sometime with the structural engineer when I was doing. So just to make sure for you, if you are ever trying to hands-on with FDS and structure, in FDS, Z-axis or Z-axis is always vertical direction because of gravity. By default, you can change it, but I will suggest don't change any default function in FDS. Try not to until you know how to do that one. So, but sometimes in structure, I find in structural engineers, sometimes they are using vertical as Y. So I will suggest not to do that. Try to do Z-axis because you have to maintain the global coordinates. So because I faced this error, so that's why I'm explaining this to you guys. So mainly the link between the FDS and OpenSees, because their script base is the device location. Device location is where you want to get temperatures. So this is the most important when you are putting the inputs. I will show you how the middlewares. I cannot show how it works, but later maybe I will make some videos, YouTube videos for that, but I will show you how it looks like. So for FDS to OpenSees, you can use different boundary conditions to get the conduct the heat transfer analysis to get the temperature for structure analysis. You can use adiabatic surface temperature, or here I mentioned AST. You can use heat fluxes, which you can get from this output, and you can even calculate heat transfer coefficient, convective heat transfer coefficient with the time varying. So time, temperature, history of all these three elements: adiabatic surface temperature, heat flux, and heat transfer coefficient. And you can use even gas temperatures. Gas temperature is the nearest cell to the structural boundary. So you might be wondering why I put the star here. There's no star in this. The main meaning is there because these above devices like adiabatic surface temperature, heat flux, and they are usually called solid phase device. So they are basically connected to the solid. So in FDS, when you are using the solid phase device, you have to mention the direction, orientation of the devices, which is a little bit critical. Otherwise, your simulation will not work. So here, like it's positive X direction. If your device direction is X direction, you say +1, negative -1. Similarly, 2 and 3, plus and -1 for Y and Z axis. So if you see this file for adiabatic surface temperatures, it's again solid phase device. So you have to mention what is the orientation of your thermocouple in FDS and structure. So this is very critical if you are using these three boundary conditions. But when using gas temperature, you need not to provide this orientation index of orientation, or you call IOR. You need not to provide, so you can use. But sometimes for structure, most of the paper I see, they're asking for adiabatic surface temperature, but they have all drawbacks. For that one, you can see one of the review paper I wrote. So I mentioned that why sometimes which input is much better and what is the limitation of each input. So you can use this, but anyway, you can use any of these devices in this OpenSees plus FDS in OpenFire. So to generate, as I said, to couple these both OpenSees and FDS, I create few modules which is written in Python programming language. So it can create, as I say, it create different script files. For example, you have FDS device script, which has all information of all device. It has which XYZ and orientation. You can, and at the same time, it will create the heat transfer script, which is generally look like this. So it has all information there, and it will create the element set. So you know where your temperature data is going. So all this information can be created by one middleware, and another module of the middleware can convert data in FDS to OpenSees format. And to put the data, I created some graphical user interface for data inputs. So for example, here, this is the script generation where you can put inputs. So here you just put some input like what is the unit. Usually in FDS by default is again in meter. So sometimes you don't go millimeter and this thing. So this program can give erratic results. So you have to mention clearly what unit you are using, meter or mm. So, and then here you will provide where you want to get data, where x-axis, what is the x and y. So like for length of the beam, you just give the minimum value of x and upper value of z. So it will create equal distance, how many devices you needed. So it will create automatically. And when you put the save file, so it will create all 3 script files automatically. But before doing that one, you may have to provide, and also you provide like what kind of entity you have. I think this one we discussed in previous topics in there, whether it's an I section, whether it's a block or a brick, and sometimes you have to write a user-defined entity. And you want to do 2D analysis, 3D analysis, and different elements, structural components, and we are using like a increment direction X, Y, Z, or you're putting like a beam column element or shell elements. You have to mention all these things there. In this GUI, you can put. And also in OpenSees, you can give the automatic inputs that what material you are using, concrete, your carbon steel, all where you need the data on the faces or you need the points and the nodal points. So all this information can be provided in this GUI inputs. And you can provide which of the entities you have. So you just give the centroids and you give the some input values through that one, because you want to create automatically an heat transfer script file. So once you have provided this information, again, when you are converting data, so to convert data transfer, you have to provide the information what input you need to carry out the heat transfer analysis. You're using AST, like adiabatic surface temperature, where your value of convective heat transfer coefficient is fixed. And you can use heat flux, where it's fixed. H, where AST plus HTC, of course, heat transfer coefficient is varying. So you can have like 6 different boundary conditions which you can transfer the data. So in the 6 ways you can do heat transfer analysis with a different boundary condition, but you have to mention it what you want to calculate. Which boundary condition, which time temperature history, or you need to conduct heat transfer analysis. So this is, it will just take the output from FDS and will convert based on the input you need. So to understand how FDS plus OpenSees is capable compared to other commercial packages and how it can represent the experiment, we did some validation cases. This is one of the cases where the localized fire has been conducted. It was conducted by Kamikawa in Japan, so where the fire was existed. So fire was burned in the burner and it was exposed to a one hollow column, and it was exposed. So the temperature results, if we done with the OpenSees plus FDS and Abacus, you can see the results with the experiment is quite close, and OpenSees plus FDS gives the almost similar or better result than the commercial packages in the validation cases. I think validation case you can find on our GitHub page as well. In another validation case we did for the smoke layer effect, which is Wakamatsu, is also Japan that tested, and to understand how the smoke layer gives higher the temperature increase. So we have some experimental data. So we try to validate with our FDS as well. And this is the result we get for different fire values, like when you are using different heat release rate, 525, 848, 1147. So the result when the smoke, where the smoke layer is very close to the experiment, but when we are talking about the flaming region, it might not matching because we do not have the enough data for the experimental, because again, this is the limitation when we do not have full information for FDS. You may don't have information what is the suit, you don't know what is the information, what was the humidity, and these many small variation can change the results. So that's what I want to say, that sometimes that's you have to be careful what when you are using inputs for FDS. So this is only to present this thing that, but in here, when you have condition is more steady state, quasi steady state, you can have the result which is matching with the experimental results. And we did also with to understand the experimental, some real accident also. So we use one case of the bridge failure which had occurred in Alabama and USA. So we try to match with some result which another researcher he did with the abacus. So we try to match with the different fires with megawatt fire and 1.5 megawatt fire and see when this bridge fail. So we use 1 megawatt fire. So this is abacus result and this is OpenSees result. It's almost same. What the bridge was failed almost 12 minutes. And so we used like 1 megawatt fire. So this bridge was failed after the tanker hit this bridge. It was failed around 12 minutes. So our result is almost very close what the real accident showed. So again, it is showing almost similar or sometimes better result than commercial software as well. So this is just want to show the capability of OpenSees plus FDS, and also that it is again open, it is free, and it is so but before we go further, we should, what we are using, we should know the limitations as well. What is the current limitation is, first, the mesh size on CFD domain must be smaller than, like, spatial resolution, like you need a temperature data for every, like for example, half meter. So your mesh of the CFD should be lower than that, because the values you are getting, temperatures or any adiabatic surface temperature, you are taking the FDS is calculating the average value of the cell volume. So it should be smaller than the spatial resolution you need for the structure analysis. So for example, again, if you are in one temperature every 0.5 meter, so your mesh should be less than 0.5 meter. Okay, and another is the limitation of OpenSees. It has, at this moment, we cannot solve the cavity radiations, and it is again under development. We will maybe add later. And at this moment, we have only few default entities at this moment, for example, block, I section, and some others. So, but you can use user-defined entities which can be generated. So these codes, all codes are available on my GitHub page. You can download and you can add that one. You can hands-on, you can work on this. If you have any question, you can just contact me. We can work on that. And we did another version with Anwar and I. We did this one with the Git version as well, where you use a Revit, and you can use some the structural model, which is at the Git, which can where a structural engineer can provide the thermocouples or there where he needs the temperature, and it can provide the thermocouple file to FDS, which is already take the geometry from Revit model, and then again the further process is same. It will get the gas temperature and convert the middleware part where you convert the temperature data in the format of OpenSees, and you can do structure analysis. So let me tell you what is the difference between two parts. One is with OpenFire, which has using a script, and was OpenFire with GID, because as a user, because you would be user or industry people who want to use, they must know what they can get from both. So first of all, again, for OpenFire, which we are discussing with the script one, they do not need to buy any license, even for a very large geometry. It's completely open source and freeware. But for if you're using for OpenFire with Git, if you have a large geometry, like for example, you're building a like for WTC building, then you may need to buy a license for that. And it's again, OpenFire is a script based. So, but and GID, as on was showed in the beginning, that they have a pre and post processor GUI. And but OpenFire, it has many inputs. At the currently, you can use different like adiabatic surface temperature, heat fluxes, adiabatic surface temperature, and heat transfer coefficient. So have number of inputs for a boundary condition to conduct heat transfer analysis. On contrary, though, when we are doing with GID at this moment, we have only gas temperatures. And I will explain you why this that one. Because at this moment, what we did not add the index of orientation. So the orientation of the thermocouples, which I told is required when you're putting some different heat solid phase devices. So at this moment, we are using only gas temperatures in GID version. Maybe we will add, or maybe some people among you will learn and add those. I hope so. But again, this is for ideal for research and because again, you need not to buy a license and for small projects. And this another one, OpenFire with GID, is very ideal for the large and very complex geometry, because you just keep the gas temperatures and easy. You need not to do some process. It's easy to see. And the boundary files in FDS, you can, because if you sometimes you need the temperature or thermal data at different location after doing fire simulations. If you want data from different location after you did simulation, you may have to redo the simulation if you want different places. But when you are using a boundary files, which is another method, again, you can find on my GitHub page. So you use a boundary file or slices, you can avoid redo the fire simulation, and you can use different location for taking the thermal data, which is again currently not in OpenFire with GID version, which we may add again. But you should know why I'm telling this one. So you should know what is the current limitation, so that maybe when you complete the research and you don't know that this was the limitations, or you may have to develop again. So let me summarize what I was talking. So first, which I try to tell you that why sometimes CFD is required for structure analysis, and with a couple with the OpenSees and FDS here. And this is the first and only open source and freeware package for structure analysis that I can see. We can see proudly for that. And we have a GUI for the middleware that makes life much easier. Otherwise, if you're doing for the script that you're writing, maybe you can do mistakes. But here where you have a GUI, it makes researcher and engineer life easier, definitely. It did for mine. And we did some validation cases to show this capability, and we discussed about some limitations as well that can be, I hope we researchers, as a researcher, all you people are here in the workshop. I wish you guys can start also, and we can join this OpenSees for Fire community, and we can develop and resolve some limitation in the future. And we talk about, we have both version for OnePlus with GID as well. Then you can use which the GID, which and what again discussed in the first session. So these are some useful links for OpenFire project you can use for OpenSees and OpenFire. Again, on my GitHub page and on my website, you can go there. I made some videos as well long time ago, but this code is a little bit changed. But in those my previous videos, you can go and check how you can make modification in the code. So you can download the course and you can make some modification in the codes based on your requirement. So all are open source, you can get it and download from my GitHub page. All these for the middlewares or everything, or Python, and it's written in the Python programming language. So that's all from my side, and you can contact me anytime you want to discuss about the FDS plus OpenSees. This is my email ID is here. So any questions, I'll be happy to answer. So I will keep this slide. So if you want to take my email ID, you can take it. Thank you very much for listening, and I will welcome your questions.
Thank you very much, Atif. Any questions from the room? Yes.
Can I use the mic or?
Yeah, come use the mic.
Hi, Atif.
Hi.
My name is Qingfeng Xu.
Yeah.
And first of all, thank you very much for the very nice presentation. And
Thank you.
it's very detailed and well explained. And I have a very general question for you. It's not about a very specific area. When you talk about the boundary conditions, you mentioned the epistatic surface temperature, the heat flux, and the gas temperature, etc.
Yep.
I just want to know from your experience, if if you or me, if you really need to recommend a bundle condition, which one will you choose? And yeah, which one you think it works better? Like fit the experimental results more well, or I just want to know which bundle condition works better. Thanks.
Okay, that's a very good question for this one. Because I said that all methods have some limitations and have their own the way they are simplified. For this adiabatic surface temperature and heat flux and other gas temperature, I wrote about their limitations in my limitation and in my review paper. If you get time, please check that one. So, but again, answer to your question. So I did one analysis where I use this first four, as you see in the slide, first four. So I find that when you're using adiabatic surface temperature, it is giving better result rather than when you're using heat flux. So somehow it is because I think FDS calculate adiabatic surface temperature more better, because I can explain the reason. Because in heat flux, most of the things usually they are calculating this heat transfer coefficient is how this FDS what is it called, it's average the value, because the boundary layer is much smaller than the mesh size. So the way it is averaging the value, it's not correct, or it's not justifiable. So again, I will say that in this value, the adiabatic surface temperature is better. But if you want to do, if I try to with the gas temperature as well, so temperature difference, but like when it goes to higher values, like when you have 700 degrees Celsius in AST, you have like 618 gas temperature. That's not much big difference, but if you're using only gas temperature, it makes life much easier because you can use the gate. So I will say that either gas temperature or adiabatic surface temperature, you can go any of this boundary condition.
Yeah, thank you very much. It's also a relief to me because I'm also doing the coupling research between
Yeah,
the
sure, great.
structure. Yeah, and
Yeah,
also
you can discuss with me then.
yeah, and also that because I'm using the adiabatic surface temperature as my input, so
Yeah,
it's
that's
very
fine.
glad to know that they also think it works quite well. Because
Yeah,
when I try to switch the adiabatic surface temperature to the heat flux, I find a lot of variations from between the data transfer.
Yeah,
So
it
that's
is.
why I don't want to use the heat flux. Yeah,
Yeah,
that's
heat flux
remarks.
has a problem at. So again, that's why I say you can see the review paper why heat flux is my open fire paper, why heat flux can not give you a better result. I explained the reason for that. And again, even you are using adiabatic surface temperature, you should know it's how the way it is simplified, because most of adiabatic surface temperature are using emissivity 1, and second, it is using configuration factor or view factor 1. So you have to be careful also when using adiabatic surface temperature, like when you have like far field in a room. So maybe adiabatic surface temperature will not give you, because your emissivity cannot be 1 at that moment, and if your room compartment is not like rectangular or something, so your view factor cannot be 1 as well. That's in the complex domain. So you can do, but you have to justify the value why you're using this.
Yeah. Okay. Thank you very much. Thank you.
All right. Any last questions? One more question. Fantastic. Atif, do we have any? Atif, thank you so much for your time, and thank you for joining us all the way from New Zealand.
Thank you. Thank you for inviting me.
All right. We have now our last presenter of this workshop, my wonderful colleague, Jin Chiu, and she will give us a talk about composite floors in fire. How's everyone holding up? We still have some coffee outside, so.
Okay. Good afternoon, everyone. My name is Jing Qiu, and now I will show you how to model composite slabs in Fire within OpenSees for Fire framework. I will present it from the following three aspects. Firstly, what is composite slab and why is it difficult to model? And then I will show you the existing numerical models for composite slabs. Last part, and of course, it is the most important part. I will show you the evolution of composite slab models within OpenSees for Fire framework. Okay, for the first part, the composite slabs contains the concrete, the lowest profile steel decking, and the upper anti-crack steel mesh. It makes good use of the mechanical properties of concrete and steel. Of course, the profiled steel decking can act as a formwork, so the application of composite slab can largely reduce the work for formwork on the construction site. The composite slabs can be connected to the lower steel beam through the stud shear connections. Composite slabs have been widely adopted, and it can be seen in some steel structure workshops, in some office buildings, and in some infrastructures. However, due to the existence of the rib, it makes the cross-section of the composite slab in the direction perpendicular to ribs non-uniform, and this kind of non-uniform cross-section is difficult for us to simulate it. Of course, we can simulate the non-uniform cross-section using the solid element. However, the application of solid element will bring another question. That is, it's too high computation cost. During the past few years, some researchers tried to propose numerical models for composite slabs, like the Greenland model. Actually, in this model, it takes the upper composite slab and the lower steel beam as a whole. So users have to define three kinds of different sections, and then we need to designate the sections to the corresponding element. That is the combination of shear and beam model. In this model, it simulates the upper continuous flat slabs and the lower ribs separately. So large quantities of rigid links will be needed in order to connect the continuous flat slabs and the lower ribs. Someone proposed to model composite slabs as equivalent flat slab. However, the biggest problem for this model is that it cannot simulate the different temperature profiles for the ribbed section and the flat section. Recently, the alternate stripe shear model was proposed. In this model, it can define the ribbed section and the flat section separately. Also, it can model the whole composite slabs using only shear elements. However, due to the different thicknesses between the rib section and the flat section, void material is still needed when we define the flat section. So we want to ask, whether can we propose a modeling approach which can model the composite slabs with high computation efficiency, accuracy, and reduce the modeling efforts. With this problem, we start to explore the evolution of composite slab models within OpenSees for Fire framework. Before we started to propose modeling approach for composite slab, OpenSees for Fire had already provided very good foundation for slab modeling. two types of shear element. There are shear MITC for thermal element and the shear NNDKGQ thermal element can be used to model slabs. For the shear NNDKGQ thermal element, it takes the geometric nonlinearity at large displacements into considerations. And two kinds of layer section can be used to define the slab section. For the multi-layered section, it allows as many layers as needed can be defined. More importantly, different layers can be designated with different material properties. From the material level, the material models for steel and concrete have been well equipped. The basic idea to model slab is to discrete the section into multiple layers. Also, for the rebars, it can be smeared into one or more layers. Users just need to designate the tag, the material tag, and the thickness for each layer, and the reference plane for the section will be at the midplane of the section by default. And the reference plane is aligned with the plane of node. So the flat slab model looks like this one. Here, we take the flat slab as an example to see the specific definition for flat slab. The slab has a total thickness of 100 millimeter. The steel mesh made of cold drawn steel was distributed at a distance of 25 from the bottom surface. It is subjected to a uniformly distributed load, and which will maintain during the following fire exposure. So we just need to define the steel and the concrete. The steel isomer can be used to simulate steel at high temperatures. Also, two types of steel, they are cold drawn steel and hot rolled steel, can be defined. Derived from the anoxide steel material, we can create the rebar material through this plant rebar thermal. When we define the reinforcement material, we have to designate the angle between the rebar direction and the global x-axis. For the concrete, the CDP plane stress thermal material is often used to model it. For the CDP concrete material, it can record the damage of the concrete. Then we will define the slab section. We need to designate the unique section tag and the total numbers of layers. And then we can define each layer by designating its material tag and its thickness. The uniformly distributed load can be applied to the composite slab, can be applied to the flat slab model as a node load or as an element load, because the ambient load will maintain during the following fire exposure. So we need to use the command of load const to set the load maintain and to set the time in the domain to be 0. When we apply the thermal load, it is possible to import the temperature data from an external file as long as we indicate the file name, and then we need to designate the bottom and the top coordinate of the section. With the basis for modeling flat slab, we proposed the first version of composite slab model, which is actually an approximated composite slab model. As mentioned previously, the reference plane for slab section is at the middle plane by default, which is also aligned with the plane of node. So if we define the ribbed section and the flat section separately by following the traditional define method, the curve section will be like this. Obviously, this is not what we want. So we proposed to offset the reference plane of the ribbed section in order to model the composite slab section appropriately. Then the composite slab model will look like this. However, in this modeling approach, the capital ribs is simply considered by using an equivalent thickness, as we can see here. Also, for the web steel decking, we ignore it in this model, so it is not an accurate model. We can take a look at the section definition in this modeling approach. The section definition is quite similar to that when we define the flat slab, except that we need to define flat section and ribbed section separately. Also, when we define the ribbed section, we have to add the keyword of offset, and we need to define the offset distance. The ribbed section and the flat section will experience different sum profiles at the same time. So before we apply load to the composite slab model, we need to identify the elements for ribs and the flat parts firstly. And then we need to apply the corresponding temperature to the corresponding element. It should be pointed after that. Due to the reference plane in the ribbed section is offset, so when we define the bottom and the top coordinates, we have to calculate it more carefully. So now, in the first version of composite slab model, we can define the ribbed section and the flat section directly, and we can model the curve section with non-uniform thicknesses only using shear element, the offsetting its reference plane. However, in this modeling approach, the capital ribs are considered simply using an equivalent width, and we ignore the web profile steel decking. To address these two limitations, we proposed the second version of composite slab model. In this model, we considered the capital ribs based on area equivalent method. Also, the web profile steel decking is modeled by the distributed steel layers. Because when we define the slab section, we cannot change the width for each layer. However, we can use an equivalent thickness for each layer to simulate the capital ribs. As a result, the concrete layers in the lower capital ribs are no longer continuous, and then we can distribute the steel layers, representing the web steel decking between the concrete layers. In order to make sure that the mechanical properties for the ribbed section is not changed, when we define the ribbed section for each layer, in addition to designate its material type and its thickness, we still need to specify its local coordinate. So in the second version of composite slab model, we can consider the capital ribs more accurately. And also, we can consider the web profile steel decking by using the distributed steel layers. However, when we use this composite slab modeling approach to simulate the composite slab in a global structure, we have to distinguish where is the rib and where is the flat part when we define node element as well as when we apply load. So we want to ask whether can we propose a more efficient modeling approach to make it easier to model composite slabs. With this question, the third version of composite slab model was born. Compared with the two previous composite slab models, the biggest feature for this version of composite slab model is that we encapsulate the ribbed section and the flat section into one integrated composite section. So when we use this modeling approach to simulate composite slab, we don't need to distinguish where is the rib and where is the flat part anymore, because the element in this modeling approach is uniform. So the application of the composite slab model with integrated composite section simplifies the modeling process for composite slabs to be as simple as when we define flat slabs. On the basis of section definition in the second version of composite slab, we just need to add one line of code to define the composite section. It is worth noting that when we define the composite section, we have to define the length ratios for the two subsections, because for the composite section, it actually contains two subsections, the ribbed section and the flat section. Another problem we need to address in this modeling approach is that, as we mentioned previously, the providers, the ribbed section and the flat section will experience different sum profiles at the same time. So when we define the sum load, we have to define two versions of sum load, and then the order for the sum load should keep consistent when we with our order when we define the composite section, such that the appropriate sum loading can be applied to the subsections. In order to present the simplification, when we use the third version of composite slab model to simulate the composite slabs, this we compare the script for simulating the same composite slab when we use the second version of composite slab model, and when we use the third version of composite slab model, we can see that for each part, from define node to define element, and when we apply ambient load and when we apply sum load, the lines of code needed can be greatly reduced. Of course, it's important that for us, at the same time, when we try to improve the modeling efficiency, we cannot sacrifice the prediction. As shown in these two figures, we can see that the central deflection time curves computed by the integrated model, which is actually the third version of composite slab model, are nearly overlapping with that computed by the stripe model. The stripe model represents the second version of composite slab. Also, both of the computed results by the two models show reasonable agreement with the test results. The application of the integrated composite section breaks through the limitation on meshing in the direction perpendicular to ribs. Also, so we can use rough mesh size to simulate the composite slab the application of rough mesh size means the reduction in the number needed to model the same composite slab. Also, when we use the rough mesh size, the needed computation time can be greatly reduced. Now, those research works have been presented in the journal paper, and one has been published in the engineering structures. Another one submitted to computers and structures is still under review. More details related to the amplification can be found in these papers. Okay, now we can conclude that in the first stage, in order to model the composite slab, we proposed to offset the reference plane in the rib section such that we can model the composite slab only using shell elements. Then in the second stage, we considered the tapped ribs and the web steel decking. In the last version, we proposed to use the integrated composite section to improve the modeling and the computation efficiency. Okay, that's all. Thank you.
All right, thank you so much, Jill. Questions from the audience? Any questions from our online audience? All right. Theo, thank you so much for your wonderful presentation. Stay. Thank you all for joining us on this workshop. We look forward to seeing you tomorrow. We are having breakfast out as I think at 8:30 in the morning. So if you don't need, you can come and have breakfast here if you want. We have coffee and everything early in the morning. We'll have our first day of the conference tomorrow. Again, thank you so much. If you'd like, we can all take a photo here now. Atif, join us on yeah.
Yeah, am I on TV?
On the TV.
Yeah, put me on
Put them on this
TV.
TV, guys. And people, you can all come and we'll take a photo first with Atif, and then okay, we'll take a photo there in the back. Atif will be in the TV. Okay, we'll take a photo in the back. Those who are joining us online, thank you so much for being with us. I look forward to seeing you tomorrow. All right. Someone should take a photo of Atif on all the TVs.
No need. Just take it your normal picture. Okay. Just saying. I can say I was in a conference still.
Get a photo of Atif. Yeah, we'll do more than one. All right, look at our cameraman. Closer. Where are the workshop presenters? You? Okay. Where is the two? Who's here? Oh, okay. CC. Okay, there's somebody behind. Can you see everyone? Is everyone clear? Oh, it's okay. It's legal to take a mask off for a photo. By the way. It officially was on the phone. Okay, look at my list. 3, 2, 1. Another 3, 2, 1. Okay, now put your mask back on in case it wasn't legal. Okay. Now look at me. 3, 2, 1. 3, 2, 1. Okay. Okay, now with artists. It's we're all cool here. Like, we don't mind. Ready. Fine. It's not so.
Get ready, Adi.
Yeah, I can you see me?
Yeah. We get much, I think. Okay, everyone, and me. 3, 2, 1. Another 3, 2, 1. 3, 2, 1. Okay.
Okay, thank you.
Thank you, everyone. See you tomorrow morning. Okay, see you tomorrow. Hey,
So what's this?
自然进来之后，然后的 mate。电脑用咱们端吗？
He just last time, like when we take a picture.
Hi, Arthur. We will.
Hello.
There's questions saying, how they get the PDF certificate.
So it's done?
Yeah, it's finished. It's finished.
Okay, great.
Yeah.